We present the lipoprotein cascade, explaining how fats move around the body from the moment they pass into the enterocyte to the formation of lipoproteins, along with the uptake of LDL and the role of HDL. We begin by discussing how fats in your intestines are packaged into chylomicrons to be transported from the intestine elsewhere. During the process of breaking down fat globules, micelles are formed. These micelles are important in transporting various products from the vicinity of the fat globules to the surface of the intestinal epithelium. These include monoacylglycerol and free fatty acids, which can be esterified to form the triglyceride, phospholipids, cholesterol, which enters via the Niemann-Pick C1-like transporter. This is important since ezetimibe, a drug that inhibits this transporter, reduces cholesterol absorption. Fat-soluble vitamins can enter as well. The intestinal epithelial cell produces apolipoprotein B48, where the components we just mentioned earlier assemble with this ApoB48 and form a nascent chylomicron. It is called nascent because it has not received everything it needs to function, as we shall see later. But this nascent chylomicron is secreted out of the enterocyte, enters the lymphatic lacteal, and travels via the lymphatic system through the thoracic duct, which eventually empties into the bloodstream. The nascent chylomicron in the bloodstream meets lipoprotein that goes by the name of HDL, that is, high-density lipoprotein. It is called high density because it contains a bunch of apolipoproteins such as ApoA1, ApoE, and ApoC2, and less fat than other lipoproteins. How HDL is formed, where does it come from, and what else it does, and why it is called good cholesterol by people, we will cover at the end of the video. For now, what is important is that the HDL bumps into the nascent chylomicron and transfers ApoE and ApoC2 to it. We shall find out what's the function of these apolipoproteins later on. The functional chylomicron now continues on its journey through the bloodstream. The chylomicron passes through blood vessels in the tissues, where it encounters the enzyme lipoprotein lipase. This enzyme is secreted by tissues and then attaches itself to the luminal side of the blood vessel endothelium. The ApoC2 on the chylomicron activates the lipoprotein lipase. Because it is a lipase, it degrades the triglycerides that are found abundantly in chylomicrons into monoacylglycerol and fatty acids. These can enter the tissues, like fat cells for example, and be re-esterified into triglycerides or used for energy production. Each time they lose some triglycerides, the chylomicrons shrink a little. They continue passing through tissues, losing their triglycerides and shrinking more. Over time as well, the ApoC2 is returned to HDL, changing the chylomicron into what is now a chylomicron remnant. The chylomicron remnants travel to the liver sinusoids, where they bind to LDL-related receptors on liver hepatocytes. These receptors recognize the ApoE on the chylomicron remnants. The chylomicron remnant is then endocytosed. Now, lysosomes containing hydrolytic enzymes can fuse with the endocytosed remnant. In the meantime, the receptor can be recycled back to the plasma membrane. The lysosomal enzymes degrade the chylomicron remnant, giving amino acids, cholesterol, as well as fatty acids. Cholesterol in the liver has several fates, including being inserted into the plasma membrane, converted into bile acids via a series of reactions, packaged into VLDL, as we shall see next, and some is also excreted into bile. As promised, we shall now continue our story looking at VLDL, that is, very low density lipoprotein. It is called that since it contains a lot of fat, predominantly triglycerides. VLDL is produced in the nascent form in the liver. Again, just as we mentioned with chylomicrons, it has not received everything it needs to function. That's why it's nascent. The nascent VLDL contains an apolipoprotein called the ApoB100. Remember that chylomicrons had ApoB48. Indeed, the chylomicron's ApoB48 is just a shortened version of the ApoB100 protein. The nascent VLDL then passes into the liver sinusoids and travels in the bloodstream. Again, just as with the nascent chylomicron, the nascent VLDL receives apolipoproteins, ApoE and ApoC2, from HDL. The VLDL can now interact with lipoprotein lipase in capillaries in the tissues, which degrades its triglycerides, just like with chylomicrons. The VLDL, however, is further modified in the circulation by the action of cholesterol ester transfer protein. This enzyme mediates the transfer of triglycerides from VLDL to HDL and cholesterol esters from HDL to VLDL. In this way, the HDL gets more triglycerides and the VLDL gets more cholesterol esters. We shall see what happens to the HDL at the end of the video. For now, we continue with VLDL. The VLDL continues traversing through the circulation, losing more triglycerides. When HDL bumps into it, taking away its ApoC2. This lipoprotein is now known as IDL, intermediate density lipoprotein. The IDL travels to the liver, where about half of it is taken up. The other half, on the other hand, has its triglycerides degraded by hepatic lipase and is converted to LDL, low density lipoprotein. The LDL contains a whole lot less triglycerides than the original liver produced VLDL and contains less ApoE. The LDL then passes into capillaries and tissues, where it binds to LDL receptors on tissue plasma membrane. The LDL receptor recognizes the remaining ApoE as well as ApoB100 on the LDL. The LDL is then endocytosed. Meanwhile, the LDL receptor is recycled back to the plasma membrane. A lysosome containing hydrolytic enzymes fuses with the LDL-containing vesicle, breaking down the LDL molecule, giving resultant amino acids, fatty acids, phospholipids, and importantly, cholesterol, whose important effects inside the cell we shall discuss now. First of all, cholesterol decreases the transcription of LDL receptors, which leads to less LDL receptors being inserted in the plasma membrane. Now, LDL can't bind and be internalized, and so more LDL remains in the bloodstream. This is essentially sending a message which says, hey, we've got a lot of cholesterol inside of us, we don't really need more. Secondly, cholesterol affects the enzyme HMG-CoA reductase, which normally converts HMG-CoA into mevalonate, a precursor of cholesterol. Well now, since the cell just got a delivery of lots of cholesterol, the cholesterol reduces the transcription of HMG-CoA reductase, resulting in lower HMG-CoA reductase levels, and so less new cholesterol is formed. Lastly, cholesterol increases the activity of acyl-CoA cholesterol acyl transferase, ACAT. This enzyme grabs the cholesterol and esterifies it with a fatty acid to form the cholesterol ester. This cholesterol ester can now be stored in the cell. Thus, overall, increased levels of cholesterol cause, number 1, decreased uptake of LDL cholesterol, number 2, decreased production of cholesterol by the cell, and number 3, storage of the cholesterol. As promised, we now finish off by delving into more detail on high-density lipoprotein, also known as the good cholesterol, starting off with its production. The production of HDL is not super well understood and a bit complex, but in general we can say that nascent HDL is produced in the liver, but also a bit by the enterocytes, as a shell containing apolipoproteins such as ApoA1, ApoC2, and ApoE. HDL can also be produced from free ApoA1 in the circulation or by budding off from other lipoproteins. We shall now examine the three super important actions of HDL, two of which we've already seen earlier, so we first turn to the one we have not discussed yet, the role of HDL in transporting cholesterol from tissues to the liver, a role that has earned HDL the nickname of good cholesterol. In the plasma membrane, cholesterol is not always found on the outer leaflet. The transporter ABCA1, however, can grab a cholesterol and transfer it to the outer leaflet of the phospholipid bilayer. This cholesterol is then picked up by the nascent HDL. In the bloodstream, the nascent HDL that has just picked up the cholesterol encounters an enzyme called lecithin cholesterol acyltransferase, LCAT. This enzyme esterifies cholesterol with a fatty acid, forming a cholesterol ester, which is less likely to escape the HDL now. In the process, a more rounded HDL is formed. The HDL travels to the liver, where a scavenger receptor, SRB1, latches onto the HDL, removing the cholesterol esters from it. The HDL itself is not really endocytosed and can continue to fulfill its functions once again. The second function of HDL we have already seen. It acts as an apolipoprotein reservoir for other lipoproteins, such as chylomicrons, where the HDL gives it its ApoC2 and ApoE, and also VLDL. The third function we have already seen as well, how HDL accepts triglycerides from VLDL and in return gives it a cholesterol ester, all mediated by cholesterol ester transfer protein in the plasma. Thank you for watching. If you have any questions, please do ask away. We here at AllNightMed would love to help you all.